Hello, this is your instructor Richard Collins. Welcome to Clouds and Precipitation, Unit 8 of ATM101 Weather and Climate of Alaska. This unit reviews the type of clouds that form in the atmosphere and the process of precipitation. Finally, I also discuss how a sling psychrometer works. In this unit, we will review how clouds are classified, review the major cloud types, the top 10 so to speak, take a look at the Earth's highest clouds, review how satellites see clouds, present how precipitation occurs, and explore how psychrometers with dry bulb and wet bulb thermometers work. This lecture supplants our textbook, Weather, a Concise Introduction by Gregory Hakim and Jerome Patou, with material from the textbook Meteorology Today by C. Donald Ahrens. Finally, I want to make one content warning. These slides include a picture of a naked zooplankton. The 10 most common clouds are shown in the illustration. These 10 clouds are divided in 4 categories. Number 1, the high clouds. Cirrus, cirrostratus, and cirrocumulus are formed of ice crystals and are responsible for optical phenomena such as sundogs and halos. Number 2, the middle clouds, altostratus and altocumulus. These are formed mainly of water droplets and some ice crystals. Altocumulus appear as rounded masses or rolls. Altostratus appear blue or blue-gray and often cover the whole sky. Number 3, the low clouds, stratocumulus, stratus, and nimbostratus. Stratocumulus appear light to dark gray with larger elements than altocumulus. Larger clouds have precipitation. Stratus are uniform grayish clouds that often cover the whole sky. They are like a bank of fog, but can be associated with light mist or drizzle. Nimbostratus appear dark and have continuous precipitation that can be rain and or snow. Finally, 4. Clouds with vertical development, cumulus and cumulonimbus. Cumulus appear as floating cotton wool with a flat bottom. They are the classic clouds formed in thermals by convection. Individual cumulus clouds are separate, unlike stratocumulus that occur in patches. Under the right meteorological conditions, cumulus can grow from cumulus humulus to cumulus congestus and finally cumulonimbus, the thunderstorm cloud. These clouds can extend from a base at a half kilometer, a third of a mile, to the top of the troposphere at about 12 kilometers or about 7 miles. In a cumulonimbus cloud, there is a huge amount of energy released due to condensation. There are strong updrafts and downdrafts, about 70 knots, 60 miles per hour, 100 kilometers per hour, or 90 feet per second. Particles can travel up and down in the cloud and grow in size, yielding large hail. These winds also form the anvil top, the cumulonimbus incus. The characteristics of these 10 clouds are summarized in the slide from What's This Cloud? The cloud codes are included. For example, CI is cirrus and CB is cumulonimbus. The slide also tabulates the values associated with the altitudes of the clouds, briefly describes the clouds, and presents the cloud structure, layers, patches, or individual clouds, and colors, white, light gray, or dark gray. The names of the clouds also use some meteorological Latin. Alto means high. Cirrus means curl of hair. Cumulus means heap. Nimbus means violent rain, and stratus means layer. Water does not condense as easily as we might expect. In perfectly clean air, water droplets do not form just because we reach a relative humidity of 100%. Like dew and frost, water molecules need a surface to condense on. Small aerosol particles, called condensation nuclei, provide these surfaces. These condensation nuclei are more than 1,000 times larger than a water molecule, so a lot of molecules can attach to them. Condensation nuclei come from a variety of natural and anthropogenic sources, resulting in the fact that polluted regions can have more fog and rain than unpolluted regions, hence the word smog, which combines the words smoke and fog. Condensation nuclei are extremely light and remain aloft for days. Condensation nuclei can be water-seeking or hydrophilic and help support water condensation. These condensation nuclei include salt particles, nitric and sulfuric acid particles. Condensation nuclei can also be water-repelling or hydrophobic and resist condensation. These condensation nuclei include oils, gasoline, and paraffin waxes. Condensation nuclei are typically 0.2 micron in size, while cloud droplets are typically 20 micrometers in size, and raindrops are typically 2,000 microns in size. In April 1986, Soviet authorities were faced with an impossible decision. Their Chernobyl nuclear reactor had exploded on April 26th, and meteorologists forecast that the radioactive cloud from the plant would cross southern Belarus and reach Moscow. If the radioactivity reached Moscow, millions of people could be harmed. Southern Belarus was much less populated than Moscow. That day, Soviet bombers set out, loaded with shells of sodium iodide, to seed the skies over southern Belarus, just north of the Ukraine, with cloud condensation nuclei. On April 27th, rains fell and the radioactive materials were washed out of the sky. Nobody warned the Belarusians of the danger, and the area is now part of a depopulated exclusion zone. A gallery of clouds showing the 5 high and middle clouds. The high clouds, cirrus, are wispy, cirrostratus, a more uniform layer, and cirrocumulus are heaped. The middle clouds, altostratus, are a uniform layer, and altocumulus are heaped. A gallery of clouds showing the 5 low clouds and clouds with vertical extent. The low clouds, stratocumulus, which are low lumpy clouds appearing in rows and patches with blue sky between them. Stratus are uniform grayish clouds, and nimbostratus appear as a dark layer and are associated with rain and or snow. The clouds with vertical extent, cumulus, or fair weather cumulus, are small puffy clouds that are the precursors to cumulus congestus. Cumulus congestus, not officially one of the 10, are precursors to cumulonimbus clouds, having more vertical extent than cumulus clouds and resemble a head of cauliflower. These clouds are associated with showery precipitation. Finally, cumulonimbus are the deep thunderstorm clouds associated with severe weather. I want to introduce a cloud that sits at the top of the mesopause. Noctilucent, or night luminous clouds, form in the summer at about 80 kilometers, 50 miles above the Earth. These clouds are also called polar mesospheric clouds. These clouds are extremely tenuous and only visible after sunset when illuminated from below against a dark sky. Visible in Alaska in late July, early August, these clouds have only been reported since the 1880s. The clouds give us insights into weather and climate of the upper atmosphere, as well as the impact of space traffic on the atmosphere. Noctilucent clouds are currently studied at Poker Flat Research Range using laser radars or LIDARs. The LIDARs yield high-resolution measurements of the clouds in altitude and time, and clouds have been detected over Poker Flat that were created by the exhaust from the space shuttle. Geostationary satellites, GOES, and polar orbiting satellites, POES, provide distinct but complementary views of clouds in the atmosphere. Geostationary satellites sit at the equator, 36,000 kilometers above the Earth. They rotate with the Earth, looking down at one spot all the time. They provide continuous observations of one region. NOAA maintains 2 GOES satellites observing the eastern and western United States. Geostationary satellites see the low and mid latitudes where they are high in the sky, much better than the high latitudes where they are low in the sky. Polar orbiting satellites move in a fixed orbit from pole to pole while the Earth rotates underneath them. At an altitude of 850 kilometers, they make 14 orbits each day, viewing the whole Earth. Being 40 times closer to the Earth's surface than geostationary satellites, they can see much more detail and see all latitudes equally well. In practice, meteorologists combine the information from both satellites to understand the weather. Infrared sensors see the heat from the ground and the clouds above the ground. Warmer objects emit more heat, following the Stefan-Boltzmann law, while colder objects emit less. As the troposphere cools with height, the warmer objects are assumed to be at a lower altitude than the colder objects. In the Arctic, interpreting satellite images can be tricky. In the visible, we have white clouds over a white snow-covered ground. In the infrared, we can have inversions where the objects in the lower troposphere are colder than objects in the mid-troposphere. So cold objects can be either at low or high altitudes. The combination of visible, VIS, infrared IR, and water vapor and other IR band images can provide comprehensive information about clouds. While the visible image shows white clouds, the infrared image allows us to determine if they are high or low clouds. The images can be enhanced to highlight the higher altitude clouds. In the images, we see low altitude clouds to the southwest of the cyclone, probably cumulus, while there are high altitude clouds along the front and to the east of the front. The thick high clouds along the front are probably altocumulus and cumulonimbus. The thin high clouds to the east are probably cirrus clouds. The water vapor tracks the cyclone with areas of humid, bright, and dry, dark air. These images show the infrared emission from water vapor in the middle and upper troposphere. Clouds are classified as warm, cold, and glaciated. Warm clouds are composed of liquid water with temperatures above 0 Celsius, 32 Fahrenheit or 273 Kelvin. Cold clouds have pockets at temperatures below freezing. Cold clouds include liquid water, ice, and supercooled water. Supercooled water is pure water between 273 Kelvin and 225 Kelvin that remains in a liquid state as there are no nuclei to facilitate freezing. Glaciated clouds are exclusively composed of ice crystals. In a cumulonimbus cloud, there can be regions of warm, cold, and glaciated cloud. In a warm cloud, liquid droplets grow by collision coalescence, where large droplets collide with small droplets and they coalesce. There is an optimum range of droplet size in a cloud for this to occur. In a cold cloud at a given temperature, supercooled water droplets have a higher saturation vapor pressure than ice particles. As a result, water vapor is deposited on the ice particles and they grow. This reduces the vapor pressure, allowing neighboring water droplets to evaporate further. Ice crystals are fragile, and so they often break apart in fragment, providing nuclei for supercooled water droplets to become ice crystals, a process called riming. Ice crystals can stick together and form snowflakes. In clouds with updrafts and downdrafts, a particle may travel a long time in the cloud, growing to large size. Eventually, droplets, particles, and snowflakes fall out, giving us precipitation. The presence of supercooled water in clouds is an aviation hazard, as under the mechanical stress of the impact of the plane with the droplets can freeze, forming ice on the aircraft wings and disrupting the plane's ability to fly. Ice particles grow as they travel through up and down drafts in the cloud. They grow through riming and eventually precipitate as hail. Hailstones range in size from that of a pea to that of a golf ball. Graupel are ice particles that are slightly cone-shaped and pea-sized. Graupel can form from riming of an ice crystal or snowflake. Crystals of different shape or habit will form under different temperatures and levels of supersaturation. Simple plates form at the highest temperatures, while more elaborate shapes form at lower temperatures. A hexagon shape is a common feature due to the angular structure of the water molecule. Clouds form at fronts where warm air rises over cold air. At a cold front, warm air is pushed up abruptly over cold air. At a warm front, warm air more gradually overruns cold air. Cold and warm fronts have distinctive weather with different combinations of clouds and precipitation patterns. At a cold front, the cold air mass is bull-nosed and the warm air rises abruptly. There is widespread rain and cumulonimbus clouds can form with thunderstorms in patches along the front. We can see that with higher wind aloft, cirrostratus and cirrus clouds separate from the anvil and blow ahead of the front. They serve as a forewarning of the storm to come. At a warm front, the overrunning of the warm air is much more gradual than in a cold front, an aspect of 600 to 4 rather than 50 to 1. Again, cirrus clouds precede the front. Nimbostratus clouds at higher altitudes produce snow and sleet, small ice pellets. As we approach the front, the clouds are lower and warmer, and the stratus clouds produce rain, drizzle, and fog. The sling psychrometer measures humidity using a wet bulb and dry bulb thermometer. The dry bulb thermometer is a conventional thermometer that measures the environmental temperature. The wet bulb thermometer is a liquid bulb thermometer with a wet wick placed over the thermometer bulb. The water evaporates from the bulb by absorbing heat from the wet bulb. The liquid in the thermometer cools, the liquid contracts, and the thermometer reports a lower temperature. The difference between the dry bulb temperature and the wet bulb temperature is called a wet bulb depression. As the environmental humidity increases, the evaporation reduces, the energy loss reduces, and the temperature drop reduces, and the wet bulb temperature increases. At 100% relative humidity, there is no evaporation, and the dry bulb temperature equals the wet bulb temperature. The wet bulb depression is 0. Tables have been computed to convert the temperatures in the depression to the dew point temperature and the relative humidity. As the wet bulb depression increases, the dew point decreases and the relative humidity increases. For example, a dry bulb temperature of 20 Celsius with a wet bulb temperature of 19 Celsius has a wet bulb depression of 1 degree Celsius and this corresponds to a dew point temperature of 18 degrees Celsius and a relative humidity of 91%. A dry bulb temperature of 20 degrees Celsius with a wet bulb temperature of 10 degrees Celsius gives a wet bulb depression of 10 degrees Celsius, and this corresponds to a dew point temperature of -1 degree Celsius and a relative humidity of 24 degrees Celsius. The E-ray temperature and humidity meter reports temperature, relative humidity, dew point temperature, and wet bulb temperature. The E-ray meter uses change of electrical properties of the sensor in the probe due to changes in temperature and humidity to determine temperature and humidity, and hence relative humidity, dew point temperature, and wet bulb temperature. The tabular values were based on a psychrometer calculator by I. Chowdhury at Texas A&M University. The calculator allows the user input temperature and then one of the three, wet bulb temperature, dew point temperature, or relative humidity, to yield all the values. The values produced by the calculator are consistent with the values from ARINS in the previous slide. Inputting the pairs of underlined values, we see that the calculator values are not consistent with the E-ray measurements. Combining the input temperature with other variables, we can see what value of temperature would give the value of relative humidity that was reported by the E-ray. For values to be fully consistent, the temperature values have to change by 2 degrees Celsius to 6 degrees Celsius. Unit 8 Summary and Takeaways. 1. Clouds are classified in 4 broad categories: low, middle, and high level, and clouds with vertical extent. 2. As regards precipitation, clouds are separated into warm and cold clouds. 3. Warm clouds are composed of water droplets and water vapor with temperatures greater than 0 degrees Celsius. 4. Cold clouds contain regions where the temperature is less than freezing and are composed of water droplets, supercooled droplets, ice crystals, and water vapor. 5. Precipitation occurs when cloud particles grow to sufficient size to fall. 6. Warm cloud particles grow by coalescence. 7. Cold cloud particles grow by freezing of supercooled droplets, by deposition from water droplets to ice crystals, by freezing of supercooled droplets on ice crystals, and by collisions of pairs of ice crystals. 8. Co-located visible, infrared, and water vapor images of clouds from satellites provide meteorological information about clouds and insights into the weather conditions. 9. Clouds and precipitation form at cold and warm fronts, and the specific clouds and precipitation that form are specific to the fronts. 10. Sling psychrometers use wet bulb and dry bulb thermometers to measure dew point and relative humidity. 11. Consistency between hygrometers and psychometric tables is not trivial. Thank you for watching this lecture.